Mike is a guy that lives on the beautiful island of Mauritius. And like many of us, his life follows a very specific rhythm. Whether it's waking up at 6 hours, having tea at 14 hours, or switching off the light at 22 hours, his daily routine is a perfectly repeating cycle. Now let's travel thousands of kilometers away to England to meet Evans. On paper, Evans' life is a carbon copy of Mike's. He wakes up, works, and eats at the exact local times as Mike, following a cycle that is identical to Mike. But here is the problem. Because of the time zones, the activities are not synchronized. England lags behind Mauritius by 4.00 hours. At the very moment Mike is sitting down for his lunch at 12.00 hours in Mauritius, Evans is only just starting his workday at 8.00 hours in England. They are moving through the same cycles of life, but Evans is perpetually lagging behind by 4.00 hours. This constant offset between two identical cycles is exactly what we mean in physics when we talk about phase difference. Now let us model the activities as a function of time so that we can understand how the concept of phase difference is present here. Let A be the activity of Mike as a function of time t, where t is the time in Mauritius. Let A' be the activity of Evans as a function of time t', where t' is the time in England. Since we know that England lags behind Mauritius by 4 hours, then we can relate the time in England to the time in Mauritius. This can be written as t' equals to t minus 4.00. For example, when t equals to 12.00 hours in Mauritius, the time in England, t' is equal to 12.00 hours minus 4.00 hours, giving us 8.00 hours. So in Mauritius, Mike is doing the activity A12.00, which corresponds to him having lunch, while Evans is doing the activity A'8.00, which corresponds to him starting to work. The time period, which is the time taken for a complete cycle, is 24 hours. This is because each man's routine lasts for 24 hours before it restarts again. If we map the 24-hour on a circle, then the 24-hour corresponds to an angle of 2 pi. That is because a full angular revolution on a circle is equal to 2 pi radians. Using direct proportion, we have 24 hours corresponding to 2 pi, 1 hour corresponding to 2 pi over 24, 4.00 hours corresponding to 2 pi over 24, times 4.00, giving us pi by 3. This is exactly what phase difference actually means. It is just an offset in time represented by an angle. We are going to denote phi as the phase difference, and therefore we have phi equals to pi by 3 in the case of Mike and Evans. Now the time t on any clock can be represented by an angle theta called the phase. Hence, we can write the phase angle theta as theta equals to t over 24 times 2 pi. The phase of Mike at time t in Mauritius is theta m equals to t over 24 times 2 pi, while the phase of Evans at time t' in England is theta e equals to t' over 24 times 2 pi. The phase difference between them can then be written as phi equals to theta m minus theta e, which can then be written as t minus t' over 24 times 2 pi. But since t dash is equal to t minus 4.00, then we arrive again at phi equals to 4.00 over 24 times 2 pi, giving us pi by 3. What we can take away from this is that any time offset can be linked to a phase difference. This can be written in the most general case as phi equals to delta t over capital T times 2 pi, where delta t is the time offset between the two periodic cycles and capital T is the time period. This equation is essentially telling us that a time offset is directly proportional to a phase difference. The same concept that we have applied to study the routines of Mike and Evans can be applied to wave motion. The routines become the oscillations of the particles, while Mike and Evans are the names of two specific particles separated by a distance along the direction of energy propagation. The time zone effect in wave motion is created by the time taken for energy to travel from one point to another. But before we look at how phase difference works in a wave, let us first analyze two objects performing oscillations side by side. Consider two objects, A and B, performing vertical simple harmonic oscillations about their undisturbed positions. As you can see, the oscillations are identical with the same time period capital T and amplitude y0, except for the fact that they don't move side by side with each other. Both objects pass their undisturbed position with maximum velocity v0. Let us denote ya and yb as the displacements of A and B, where each one's displacement is measured from its undisturbed position. We are going to look at how the displacement y varies with time t at intervals of quarter time period capital T by 4 for both objects. We will also keep an eye on the velocities of the objects, which are denoted as VA and VB respectively, so that we take into account the direction of the vector quantities. We are going to take the positive direction as vertically downwards. We start at t equal to 0 when A is at the undisturbed position. At this instant, the displacement of A is ya equals to 0, and it is moving vertically downwards at maximum velocity, which can be written as VA equals to plus V0. At that same instant, B is at the top position, where YB is equal to minus Y0 and VB is equal to 0. At t equals to capital T by 4, A is at the bottom position with displacement YA equals to plus Y0 and VA equals to 0. At that same instant, B is at the undisturbed position where YB equals to 0 and VB is equal to plus V0. Then at time t equals to capital T by 2, A is at the undisturbed position again, where YA is equal to 0, but VA is equal to minus V0. At this instant, B is at the bottom position, where YB is equal to plus Y0, and VB is equal to 0. At t equals to 3t by 4, A is at the top position, where YA is equal to minus Y0, and VA is equal to 0, whereas B is at the undisturbed position, where YB is equal to 0, and VB is equal to minus V0. Finally, at t equals to capital T, now we are a full time period later. We see that A is back at the undisturbed position, and YA is equal to 0 and VA is equal to plus V0, and B is at the top position where YB is equal to minus Y0 and VB is equal to 0. So both objects have completed a full cycle. Now let us analyze the graphs closely. What we see is that whatever object A is doing, object B is doing it quarter time period later. In other words, B is lagging behind A by capital T by 4 or quarter time period. Based on the graph of A, we can write the equation for the variation of its displacement with time as ya equals to y naught sine omega t, where omega is the angular frequency. And remember, the angular frequency is related to the time period as omega equals to 2 pi over capital T. Here we can write theta A equals to omega t, where theta A is the phase of A. Based on the graph of B, we can write the equation for the variation of its displacement with time as yb equals to minus y naught cos omega t. Now, these two equations may look completely unrelated. But if you look closely, minus y naught cos omega t is just y naught sine omega t minus pi by 2. In other words, minus y naught cos omega t is just y naught sine omega t, but delayed by pi by 2. So we can write yb equals to y naught sine omega t minus pi by 2. Here also we can write theta b equals to omega t minus pi by 2, where theta b is the phase of B. The phase difference phi is then calculated as phi equals to theta a minus theta b, which is equal to omega t minus pi by 2 in bracket, giving us pi by 2. Using the equation, phi equals to delta t over capital T times 2 pi, and substituting phi equals to pi by 2, we get delta t equals to t by 4. So, the oscillation of B is simply the exact copy of the oscillation of A, except it is delayed by a time of t by 4.